name, and we call it austenite. If the material exists at room temperature, we call it ferrite. And ferrite is what is indicated as alpha in the diagram and exists from about 0.009% carbon up to 0.03% carbon. And that is a solid solution now of carbon in pure iron. So we have an alpha solid solution, which we call ferrite. We have a gamma solid solution, which we call austenite. And in between the two, we have a mixture of alpha iron and gamma iron, or between ferrite and austenite. Over on this side, we would have a mixture of austenite and Fe3C. And in fact, if we're beyond this, we have cast irons that have austenite and Fe3C. So if you can now remember the temperatures we talked about, we go from absolute zero all the way up to a temperature that's about this particular temperature, about 1400 degrees Fahrenheit. And when we get to that particular temperature, the material becomes non-magnetic. So there would be a little dotted line to indicate the Curie temperature if we wanted to put it on there. If we heat it above that particular temperature up to about 1700 degrees Fahrenheit, still body-centered cubic, non-magnetic, and now it will change into this material, which is austenite, which is non-magnetic, face-centered cubic, and stays at that temperature until we get at a higher temperature here. This is an abbreviated diagram. There should be a peritectic reaction up here. And if we put it in, it would look something like this. That line would really be connected like that. But we don't have to worry about that in considering the solid state reactions, which we call heat treatment. Well, if you can remember the diagram now, just visualize when I talk about 1333 degrees that I am really talking about this temperature that exists right here. This is the eutectoidal temperature. That is the allotropic transformation of iron for a material that's about 0.85% carbon. Then I'm always talking about going from this material, which is a mixture of alpha plus Fe3C, to this material, which is going to be just pure austenite, single phase. Well, let us take a look then let us take a look at what's going to happen if we start heat treating material. Perhaps I'd best do this by telling you a story, because you'll remember it better with the story. Let's suppose that you were living in the West 100 years ago, and you wanted to have a chisel, a cold chisel, a chisel that you could cut steel with, or you could chisel marble with, or something like that. And you'd go to a blacksmith and you'd say, I want a cold chisel, make me a cold chisel. And I want to tell you what the blacksmith would do. The blacksmith would say, all right, I'm going to take your particular material and I'm going to convert it to a real hard material, hard enough so it'll be harder than the quartz or whatever rock you want to chip, or harder than the piece of material I made it from. I'm going to heat treat it. So first of all, he would, with his forge, he'd fabricate this chisel, hammer it out until it was the shape he wanted. He would sharpen the end of it, or almost sharpen the end of it. So one end of this chisel is going to be sharp, thin. The other end of the chisel is going to be bulky. Well, if you've ever used such a chisel, you know if you hammer on one end, it will tend to mushroom. You don't want it to spall. You don't want it to break, to fracture when you hit it with a hammer, right? So you make it tough and malleable. So one end of it will flow if you beat on it. The other end you want real hard. So the blacksmith, having the chisel like this now in that geometric shape, says, all right, I'm going to make it like you want it, hard on one end, soft on the other end. So you take this chisel and stick it in his forge, bring it up above the 1333 degree transformation temperature. He would carry the material into the austenitic range. And when he got it into the austenitic range, then he would say, all right, now I'm going to quench the end of the chisel. And he would quench the end of the chisel by shoving the tip of it in water. And the water would cool the steel off very rapidly. And it would change the structure, but it wouldn't go back to the ferritic structure we had before. It would change to a real hard substance that we will call martensite. And when that transformation occurred, he could tell when it was just right, because the end of it he could touch it with his finger. It would be cold. But the top end of the chisel would be hot. And he would polish the chisel edge with a piece of sandpaper, and he would watch. And as the heat flowed from the hot end to the cold end, the oxide of the iron would be developed, and you'd get an interference color. And he could follow those colors. And when the purple color got right to the tip of the blade, he would say, I think that's going to be just the right hardness. And he'd throw the whole chisel in the water, quench it all, and he'd give you a chisel, the point of which would be very, very hard, and the hardness would start to grade off until a very soft material at the other end. And maybe he didn't know what he was doing, but he was pretty successful at that. And let's just look at in transparency now what he was doing temperature-wise, because he did most of this not with a thermometer. He just looked at the material to tell what he was doing. And what he was doing was, he took the piece of iron, he was heating it up. It was magnetic up to this particular temperature. From here to here, it became non-magnetic. He really didn't care about that, but he looked at it and he got it into this temperature. And if you looked at that, it would be a cherry red. And when he got it to that temperature, he knew it was ready to quench, and he quenched it back into the water. Actually, if he'd heated it on up, he'd gotten into the delta region of body-centered cubic again, which would be up in here. Actually, he's transforming the material, and here's what he's going to see if he transforms the material. If he could look at the austenite, if he could take the material up to the austenitic temperature and look at it, what he would really find out is that he would have crystals. Well, that's what we'd expect. Solid state metallic materials are crystalline. And so here he has crystals. And he has crystals of austenite, and these are crystal boundaries that we find in the material. Actually, these perfectly straight lines are also crystal boundaries, but they are special crystal boundaries called twins. But all of these things are crystal boundaries, and it's no identifiably different material. The little pockmarks you see in this particular case happen to be holes in the material, but it's not a solid state phase. If he would take that particular material and very, very slowly cool it, he would wind up with this as a microstructure. Now this represents something that's about a 0.4% iron, 0.4% carbon iron. And so all of the material is not eutectoidal structure, the lamella structure. Part of it is ferrite, that's the white material. And the eutectoid itself is this lamella structure that appears in here. And we have a special name for that too. So you don't hear metallurgists talk about eutectoidal structures much in steel. What they talk about is pearlite. And when somebody says, oh, this is a completely pearlitic structure, what they mean is that the structure all consists of what looks like a black island here. What that black island is a layer of ferrite and a layer of cementite, and a layer of ferrite and a layer of cementite. But it says that all of the carbon that's in this piece of steel resides in these little dark pockets. But even within the dark pockets, it's distributed into layers of iron carbide and iron carbide and iron. Maybe you'd like to know why they call that pearlite. The reason is if we had a totally pearlitic structure, a big grain structure, big crystals, and if we polished that and etched it, what we would really have is little high points and low points, because one of the phases would etch more than the other phase. And so we would have a land and a groove, and a land and a groove, and a land and a groove. And if we have white light shining on that, we have actually a little spectrum differentiator. We have a little grating, and it breaks the white light up into its spectral colors, and what you see is all of these beautiful colors. But these lamella sections aren't perfectly straight, and so we don't get straight lines off of it, and the grains aren't all oriented differently, so we get an iridescence that comes off. And it looks like mother of pearl. Well, remember from earlier lectures, if it looks like a tree, you call it a dendrite. If it looks like pearlite, pearl, mother of pearl, you call it pearlite. So we call this material pearlite. And that's what the metallurgist means when he talks about this particular material. Well, we're going to change a lot of things as we move through the heat treatment of the material. And what we want to do is to see exactly what we can be changing, and then go back to the equilibrium diagram and find out what happens as we change the temperature. And we have to find out what's really working behind the scene in all of this. Now here's a plot of the effect of the tempering temperature on the hardness of the material. That is, if you measure the hardness of the material at room temperature, how about the tempering temperature? Because when the blacksmith heated that material up, he really went to a higher temperature. He quenched it to one material, which was the martensite, which I guess I forgot to point it on the previous slide, but I'll show it to you again in a moment, is a structure that you get if you quench it all of a sudden. This is the martensite. But if you heat the martensite up, then you get a tempered product, and we're interested in finding out what that tempered product really is. Now let's look at the microstructure again, and we find that this is the water-quenched material now that the blacksmith got for the tip of the chisel. This material was austenite. If he cooled it slowly, he'd get that, and so he got that on the upper end of the chisel. And this is the water-quenched material, which we call martensite, and it looks like this. If he reheats this material to a low temperature, he gets a structure that looks like that. And if he heats it to a very, very high temperature, he gets a structure that looks like this. Now this particular structure, if you examine it closely, you can see that the cementite is a little, in little circles, or little spheroids. And so we would call this structure spheroidized cementite. And we'd call this one tempered martensite. We call this one martensite. We call this a pearlitic structure. And this is an austenitic structure. So what we really want to do now is to see what a property change would be. And again, in the slide, we find out that we have here a plot of the room temperature testing of the material to find out what the strength of the material is in effect as a function of the tempering temperature. So as the tempering temperature goes up, and this is increasing temperature, tempering temperature, then the room temperature hardness of the material is going to drop down, or the tensile strength of the material is going to drop down. And this is for a 1050 steel. Obviously we can have a plot like that for every steel that we have. Every steel that we can heat treat, we will have such a temperature. So we have this capability now of going into the material and doing almost anything that we want with it. And for years and years and years, we just did what the blacksmith did. We did it by eye. We didn't know what we were doing. We finally learned that we could quench the material directly to a hardness level that we wanted. We didn't have to quench it in water. We could quench the material in oil, and it would cool a little bit slower. And we'd get a direct quench product that would be softer. Or we could quench it in a still heavier oil and get a still lower temperature. Or quench it in air and get a still lower hardness number on it, a lower strength level. And these direct quenchings were great, except for one thing. That is, we tend to get cracking in the material. Just visualize, if you can, a ball of steel the size of your head, and you say, I'm going to quench that. If it happens to be eutectoidal steel, and I plunge it in a bucket of water, the outside shell of that steel is going to contract, right? It's going to start to contract. It hits the allotropic transformation temperature, and it wants to expand. But the inside of the whole shell is still losing its energy, and so it's contracting. So the outside shell of the material is put in tension, in compression, right? It's being pulled together by the inside. But now the inside of the material begins to transform, and the outside of the material is trying to shrink because it's already transformed. But the inside of the material is pushing on that shell on the outside, and it can push hard enough to transform, so it'll crack the outside all to pieces. So the stuff will just blow apart, will explode. And we have shrapnel coming off from the outside, because it would be at a strength of about 300,000 psi, and we just rupture it. So we can't afford to, with a big piece, to quench it directly to martensite. We have to quench it to a higher temperature form or softer form.